Okay, welcome everybody. Thank you for coming to this talk. My name is Iqbal Khan. I am a technology evangelist at this company called Alachisoft, which is maker of a distributed caching product called NCache. Today's topic is scaling .NET applications with distributed caching. This is not a talk about NCache. It's about the actual topic of what problems does distributed caching solve and how does it solve it, and how should you go about using it. If you have any questions, please raise your hand as I'm talking so that we can have more interactive session instead of waiting until the end. Okay. And my apologies, I have a slight cough, so hopefully I won't be coughing. I've got something in my mouth, but if I do, please. So let's go through a few definitions. I'm sure most of you know this already, but just for completeness purposes, we'll first define scalability. So scalability is not application performance. It is application performance, high application performance under peak loads. So if your application performs super fast with 5 users, it is not necessarily scalable until it performs the same way with 5,000 or 50,000 or 500,000 users. Of course, if your application doesn't perform with 5 users, then you have other problems than what the session's all about. So, linear scalability is more of a deployment definition. If your application architecture is such that you can deploy it on multiple servers, and as you add more servers, the transaction capacity, and the word transaction here means activity, the requests by the clients of that application, that the transaction capacity can increase as you add more servers in a linear fashion, then you have a linear scalability in the application. If you don't, then you have a non-linear scalability, which means that after a certain number of servers, adding more servers actually slows things down, so you're stuck pretty much. You can't really buy your way out of this. So you obviously don't want a linear scalable solutions. Which applications need scalability? If you have one of these applications, then you're in the right session. These are usually web applications, ASPnet, web services, backend for IoT, big data processing through distribution, and other server applications that need a lot of transactions. These days, a lot of businesses are online, e-commerce, online banking, online everything. So any online business that has a customer-facing application usually needs scalability. That's where you get thousands of simultaneous users. Think of a bank or an airline or a social media company, and scalability comes to mind. The backend for IoT is also, all of those devices need to talk to somebody on the backend, so the backend needs scalability. Big data processing is also a very big emerging space, although my focus is .NET, and on the .NET side, the big data processing isn't as popular as it is on the Java side, but the concepts are the same. You can do big data processing through a distributed model and achieve scalability. Other server applications, you may have a large bank that has millions of customers that call every day to change address, maybe transfer funds from one place to the other, and there may be compliance issues that by midnight or by some time at night, you have to process all of those requests. So there's a scalability need where you need to be able to handle all those. So essentially, all of these are server-side applications that need scalability. So what is the scalability problem? First of all, the good news is the application tier in most of these applications scales very linearly. If you have a web application in a load-balanced environment, you can add more servers, no problem. So the problem is in the data layer, the data storage layer. What I mean by data storage is relational databases, your mainframe legacy data, your application data. The data is the one that's bottleneck. If you use NoSQL databases, they will help the scalability problem, but a lot of the time you're not able to move to NoSQL because for a variety of technical and business reasons, you have to use relational databases. And NoSQL is useful only when you move to it. So it requires you to move away from relational, at least whatever data you need to put into it. You keep it only in one place, not both. So that's why it's not always the answer, even though architecturally NoSQL is a scalable database. So you pretty much have to solve the scalability puzzle with relational databases in the picture. You cannot remove them from the picture and still and hope to achieve scalability in all cases. In some cases, yes, you can. So how do you actually achieve scalability? You deploy a distributed cache in between the application tier and your database tier or your data tier. And this distributed cache is kind of a new best practice for any application that needs scalability. It consists of 2 or more low-cost servers where they form a cluster, and that cluster actually pools the CPU, the memory, the network card resources into one logical capacity. So the more servers you add at this layer, the more capacity you have, and capacity is transaction capacity, storage capacity, and throughput in terms of the network cards. So these days, if you want to achieve scalability, you pretty much have to have this infrastructure in your application. In case of .NET applications, it's good to have all of the whole stack being .NET. And these boxes typically are not very high-end. The most common configuration that we see is a dual CPU, quad-core, basically 8 cores per cache server configuration. 16 gig to 32 gig is an average memory on each cache server. So it's better to have more cache servers with less hardware power than a few with a lot of hardware power. And because the cost also is more manageable if it is that way. Once you put this caching layer in between the application and the database, the goal is to use it for about 80% of your data traffic. So 80% of the time, you should be going to the caching tier, and 20% of the time, you should be going to the database tier. That 20% includes a lot of updates. All updates, of course, have to be done to the master data store, which is your database, and some of the reads, because the data has to be loaded into the cache from this. So keep this picture in mind. With this picture, you can pretty much scale quite a bit. I mean, we have customers who've got 50 to 100 servers in the application tier, which is pretty much the high end of e-commerce these days. Most customers have about 8 to 20 servers in the application tier. So then you have a 4-to-1 or 5-to-1 ratio between the application tier and the caching tier. That's not a limitation. It's just a best practice based on how much load the application tier can take versus the caching tier. But that ratio might change if let's say for every client request on the application tier, you have to make a lot of caching calls. Then the more calls you make per client request, the more or the less of a ratio you have to have between the application tier and a caching tier. But the minimum or the minimum ratio that we've seen is 2-to-1, and where you have 4 servers in the application tier, then you might have 2 in this. Minimum you need 2, of course, for redundancy purposes, so that high availability can be achieved. So this is sort of a case into why you should be using a distributed cache in your application, what problem it is going to solve. So let's say once you're convinced that distributed cache is going to solve this scalability bottleneck, the next question that comes to mind is, how do you use it? Where in your application should you use distributed cache? What are the use cases where distributed cache makes sense? So there are 3 categories of it. Number 1 is what I've been talking about so far, which is the application data caching. That's where we talked about that you reduce those database trips. The thing to keep in mind in application data caching is that the data exists in 2 places. One in the caching tier and one in the database. Now, as soon as you know that data exists in two places, what's the first problem that comes to mind that might occur? Synchronization. Yeah. So the worst that could happen is that the data in the caching tier is older than the data in the database, and that data is sensitive, and you really can't afford to have an old copy. And the biggest example of that is a banking application where you're trying to withdraw funds. You don't want to withdraw $1 million twice, or maybe you do, but the bank doesn't. So that's the biggest problem that any distributed cache has to solve. And if a distributed cache does not solve this problem, then you're forced to cache only read-only data. And in fact, most people, when you talk to them about caching, think of caching as a read-only store, where the data doesn't really change much. Did you have a question? Okay. But in reality, you want to cache as much data as possible. That means both read-only data, data that does not change very frequently, but it still changes, and data that changes very, very frequently. All data has to be cached. That's the only way to really benefit from that use case. And I'll come back to how you achieve that. Number 2 use case is if you have an ASP.NET application, then there is some ASP.NET specific caching that you can do. The most common is the sessions. And that's also the easiest to use also. The second is the view state. If you are not using the MVC framework in ASP.NET, then the second use case would be the view state. View state, for those of you who don't know what view state is an encrypted string that gets sent by the browser, by the server to the browser, only to come back in case of a postback. So that heavy string, which might be 1K to hundreds of K, travels all the way to the browser, and maybe on the next call comes back. So it's an ideal case for caching. If you could just cache the entire view state on the server side and only send a small key, it would speed up your overall application quite a bit. It will also save you a lot of bandwidth cost. Bandwidth is not cheap in terms of how much data you're going to consume. The third use case in ASP.NET is the page output. So if your pages are not changing every time, why execute them again? Every time you execute a page, you are consuming all those resources, CPU, memory, all the back end, you're making the database calls, all of that. But if the output is going to be the same, why not just display the output from the last execution? Microsoft ASP.NET Framework has an output cache capability where you can plug in a distributed cache so that the same capability is going to be available in a web form. In case of ASP.NET, the nature of the problem completely changes. In case of ASP.NET specific caching, of course, you will do application data caching also from within ASP.NET, but I'm categorizing that as separate. But other than the application data caching, the ASP.NET specific caching, the data exists only in one place, which is the cache. There is no database. You don't store those sessions in the database if you're going to put them in the cache. So the cache is the master store. At the same time, the data is transient. When cache becomes a master store, what's the biggest concern you have? What might happen if cache is the only store? Yeah, you might lose the data because cache is in memory, and memory, as you know, is volatile. So if you put data in the cache, any cache where you're going to put session or other types of data as the master store, that cache has to provide replication. Without replication, if you're caching data, you're going to, you're basically walking on fairly thin ice. There's another problem, which is that memory is limited, and which is true also in application data caching. Your database might be terabytes of data, but the cache, as I said, about 16 to 32 gig per server. Maybe you have 5 or 10 of those servers, so you have a few hundred gig of data at most. So it's a subset of the database, and that's okay because you will just remove some of the data when the cache becomes full, because that data exists in the database, right? But that is not true when you have cache becomes the master store. So again, keep this in mind, and we'll come back to this, that when you're using a cache as the master store, you don't want to remove data unless that data is no longer, its life is over. So you don't want to just remove data because cache is full. You want to do capacity planning appropriately, that when whatever data you're storing, for example, if you're storing sessions in the cache, you expire sessions based on inactivity. So you say if the user is going to stop using it, if the user logs out, and after about 20 minutes of inactivity, the session needs to be cleaned up. So you need to do your capacity planning where under peak loads, the sessions are expiring and not being evicted. So the nature of problem is different. The third use case is something that a lot of people don't know that cache is really good for, which is runtime data sharing through events. Think of this as like a service bus, as a messaging platform, but it's not a replacement of message queues. Message queues have a different purpose. They can work in a geographically distributed environment. Cache, runtime data sharing is good, usually within the same data center. But within the same data center, a distributed cache is much faster and more scalable than message queues for runtime data sharing. Because of the fact that it's got multiple servers, you can keep adding more servers as your transaction capacity increases. And a good distributed cache provides event-driven pub-sub-based or pub-sub-style data sharing model. Also, other types of events, continuous querying is another feature. Distributed caches exist both on the .NET side and on the Java side. And all these features that I'm talking about, other than ASP.NET specific caching, where the sessions exist also on the Java side, but view state is ASP.NET specific, and output cache, there's, I think, an edge caching on the Java side. But these issues are common between .NET and Java. So runtime data sharing through events is a third use case that you guys need to keep in mind and use a distributed cache for that. Even there, you may have the cache as the master store, or you may have cache as a duplicate of the database. Or you may, often what happens is the database has the same data but in a different form. The cache may have it in a transient form. Maybe it's an aggregation of some data, and that aggregation needs to be shared so that it doesn't have to be reconstructed every time. So if you lost that data, you could reconstruct it from the master. So unlike the ASP.NET, the runtime data sharing may or may not have the master store as far as the cache is concerned. But if it does, then you have the same issues as I've mentioned up there. Any questions so far? Okay. Let's quickly get this out of the way in terms of how do you use a distributed cache for sessions. Because ASP.NET, actually, in anywhere, there's a framework where you can plug in. Makes your life easy because you don't have to do any programming. So where there's no framework, then you have to make API calls into the cache. And as far as the frameworks are concerned, application data caching, entity framework does not, up until EF6, there was no framework for caching. EF7 or EF1, EF Core has a caching framework so that you will be able to plug in a distributed cache without having to do any programming, and suddenly application data is being cached. But as far as the ASP.NET specific caching, all three examples that I gave, they have frameworks. Frameworks means you just use it, you just plug it in. So what happens, let's say this is your picture, you install the server portion of the cache on the cache servers. Most of the time you have a separate caching tier. Then you install a client portion, which is usually a client library, or it might even have a client-side process. It depends on the cache. So there's a client portion of the cache. And that client portion usually would have the ASP.NET Provider for the sessions. So let me show you an example of how an ASP.NET Provider would be used. I am, of course, using NCache as the example, but the same applies to any other cache, including Redis. So you would basically go into your web.config. So after you've installed the cache, and you've created the cache, and the cache itself is working, you would go into the application tier and modify your web.config. You'll do basically two things. One, you will do an add assembly of your cache's session state provider. In case of NCache, that's just a line that you copy and just put it in your web.config. For other caches, it's going to be something similar. The second thing you do is you basically create the session state tag, and then in case of NCache, just copy this, but in case of other caches, copy it from their example. And make sure your timeout is appropriate. In case of NCache, make sure you have a cache name specified. So I'm just going to, let's say, my demo cache. Oops. Whatever you named your cache. So that's like a connection string. So that's all you specify. Once you've specified this, you run the application again, and all your sessions are stored in the cache. Very straightforward, takes practically very little time. The only thing you have to do after this is do some sanity testing, go through the common use cases, make sure your application still works. The reason you want to do sanity testing is because if you had an in-proc storage model for sessions, then your session object might contain objects inside which are not serializable, and your application will still work because all the sessions are kept within the application, within the worker process. As soon as you put in a distributed cache, it's an out-of-process store. So out-of-process means serialization. So your session object is not going to serialize if the data inside it is not serializable. So that's why you want to do a sanity test to make sure that you haven't accidentally created a situation where it's not serializable. But that's about it. There's no programming needed. You just make this change, assuming that you're comfortable with the cache that you're using. You've done some testing of the cache itself. You plug this in, and the sessions are stored in it. Okay. Let's come back to application data caching, which was the main focus, which is where you'll be spending most of your time if you want benefit out of distributed caching. And as I said, if you don't have a framework, so if you had an EF core application, you don't need to make cache calls if the cache has a provider for EF core. But EF6 or earlier, the architecture doesn't support it. If you're using NHibernate, which is the equivalent of EF, which is the .NET version of Hibernate, it's an OR mapping engine, for those of you who don't know, that has a model where you can plug in a cache without any programming. But other than that, you have to make calls, API calls. These calls are NCache, which is very similar to the ASP.NET Cache object, as you can see. You connect with the cache, assuming the cache is already running, as I showed you here. The cache will be running as if it's a database. So it's a separate process. The cache is running. You connect with the cache, and then this is a cache handle that you preserve, and you use that to do cache.get. You can do get, contains, add async, insert, remove. Add means don't add it if the item already exists. Insert says add it if it doesn't exist. If it exists, otherwise no. Add it if it doesn't exist, otherwise update it. Remove, of course, is remove. The async versions of these methods say don't wait for the cache to be updated. Just come back. And as soon as you do the async, there would be an overload which will take a callback. So if something goes wrong, your callback will be called. But the async is very, very useful, and I'll actually go through some use cases where async becomes really, really useful. It's very simple, as you can see, just a simple API, cache.get, add, insert, removed. Of course, there's more to it than this, but this is the gist of it. And I'll actually show you some source code examples on how to do all of those things. Where'd that go? Okay. So let's come to application data caching. So any cache that is good, that must ensure in application data caching that the cache is fresh. That's what we talked about, right? Because the cache exists, the data exists in two places. How does it do that? The most common way is expirations. Most people know expirations. Expirations is when you're adding something to the cache, you tell it to please go ahead and expire this, let's say in 5 minutes. Let me show you an example of expirations. So let's say here's a basic, it's a console application. Again, this is an NCache example, but I mean the same rules apply. You reference the caching assemblies. You use the caching namespaces. You connect with the cache. You get the cache handle. You add the data. And as you're adding the data, you specify, let's say 1 minute. So you're saying, expire this 1 minute from now, in case of NCache. And I think this is also the ASP.NET cache object also works the same way. So there's a key, there's the actual object that you're trying to add, there's the expiration. And you're saying don't do any sliding expiration and other stuff. So by just having that call, you've specified, you've told the cache, expire this item 1 minute from now. Why do you want to expire this 1 minute from now? If you just think about it. Because you think that if you kept it longer than that in the cache, somebody's going to change that data in the database. And the cache won't know about it. And we'll have that really undesirable situation of old data in the cache. So you're making a guess, really. With expirations, you're only making a guess. So there's also a sliding expiration, which although has the same name, but the purpose is completely different. Its purpose is essentially cleanup. So for sessions, you're saying when the user logs out and nobody's touching that session, why keep it in the cache? So remove it. So there's a sliding expiration which says, remove this item after this long of inactivity. So that you don't have to keep track of it, of course. So absolute expiration is for application data. Sliding expiration is for transient data. Very, very different purposes. It's a very important point to keep in mind. And we've talked about reference data is data that either does not change, it's read-only, or it changes but very infrequently. Maybe every hour, maybe every day, or every week, something. These could be your pricing, these could be, or something else. Transactional data, on the other hand, is your customers' accounts, activities that change, maybe every 5, 10, 15 seconds, 30 seconds. And so you need to be able to handle both. And expirations, you specify different expiration intervals for different type of data. That's why you have control. But expirations, as I said, is making a guess. So although it's good for some data, it's not a foolproof system. You might still have a situation where the data changes in the database. If that happens, then you need the cache to be smart enough to monitor your database. So whatever data you're putting in the cache should be smart enough to monitor that data in the database. So if that data changes, the cache will be able to take care of it or synchronize itself. And there's a feature in SQL Server called SQL Dependency, or and there's one in the ADO.NET framework for Oracle called Oracle Dependency. These features essentially use database events. Whichever application uses these features, let me show you an example. Right. So let's say, oops, not this one. Let's say that you're trying to add something to the cache. Okay, so you're going to do cache.add. Is everybody able to see the source code? Okay. Okay. So you want to add this object. This is some product. It has a key. So, but you want to tell the cache that if the corresponding row in the product table changes, that this item should be removed from the cache. And the cache should be able to handle that. The cache can actually use a SQL dependency where it will use this SQL statement. It'll use a connection string to SQL server, and the cache becomes a client of your database. So think of this picture. Oops, hold on. This picture here. So your application is running here. It adds something to the cache, and it tells the cache, please monitor the database. So the cache opens a connection with the database and uses the SQL dependency feature of ADO.NET, and then becomes a client of the database. And from that point onward, SQL Server sees the cache as a client, and it notifies the cache through database notifications if that corresponding data set changes, whatever that SQL statement meant. And that means now you have a situation where, go ahead.
Just check, is that done so that SQL Server is pushing notifications to your cache rather than your cache polling SQL Server?
Exactly. So SQL Server is going to push the notifications to the cache. It's an event-driven model, and the cache will immediately then take an action.
And is that synchronous? The SQL Server block until it's got an answer back from the cache, or does it fire it off? And so you've still got that chance of very short interval.
You have a chance of very short interval, but usually it's fairly quick. But it's an event-driven update. SQL Server sends an event notification to the cache. The cache immediately does one of two things. It either removes that item from the cache, which is the default behavior, so that when it's removed, the next time your application wants that data, it won't find it in the cache. It'll go to the database. I mean, that's the common pattern of doing cache programming, is that you look for the data in the cache. If it's not there, you go to the database. So by removing it from the cache, it's automatically synchronized. Another option could be that it can reload the new version immediately. And I'll come back to that in a bit, how it will do that. So, again, the cache has to become smart enough that it knows these scenarios. If it doesn't, you're forced to then not cache transactional data or cache transaction data where you can really make a guess on expirations very accurately. Otherwise, you will have a situation where the data becomes stale. Go ahead.
Is there a way to maintain dependencies between the cache objects?
Yes, and I'll go into that at the end of this page. There's a cache dependency feature, which is also an ASP.NET Cache feature that some of the other caches have, including NCache. SQL dependency, let me complete my thought on that. SQL dependency is a great feature, but if you had 1 million objects in the cache that needed SQL dependency, for every SQL dependency, SQL Server creates a data structure within the database server to monitor that data set. Because that data set does not have to be a single row. It can be it could be multiple rows, it could be a join of multiple tables. I think it can be joined, but let's say, even if it's not a join of multiple tables, it can definitely be multiple rows in the same table. And if SQL Server had to create 1 million of those, you can imagine, since we're talking scalability, you have to think in large numbers. You can't just think about 1,000. So SQL dependency is great, maybe for thousands or tens of thousands of items. For hundreds of thousands or millions of items, it's not great. Another option could be, which some of the caches support, is that the cache could actually poll the database. Now, polling is not as real-time as events, but polling is a lot more efficient, because in one poll, you could just say, give me all the rows give me all the keys where the data has changed. So in one call, you can get back thousands of rows, and then you could take action on those. So it's like a bulk operation. But even that has limitations, because when you're talking millions of dependencies, that has limitations. The third option is to use a CLR stored procedure. So if the cache that you're using gives you a client library that's compatible with CLR environment in the stored procedure, either SQL Server or Oracle, Oracle on Windows, of course, then you can make the call from a CLR procedure. So the way CLR procedure works is that you don't create a SQL dependency anymore. You add data into the cache, and then then you modify your database triggers. That when that row changes, the database trigger calls a CLR procedure, and the CLR procedure now knows that this row is changed, and it knows what the corresponding object in the cache is or ought to be. So it'll either go and add or update or remove that object from the cache. So it actually is, the CLR procedure becomes a client. So it's like a reverse thing here. The database is now becoming a client of the cache through CLR procedure. Yes. The transactions, yes. So the CLR procedure is going to be called within a database transaction. And this is where those async methods come in really handy. Because if you don't have the async methods, and you're calling multiple servers to be updated, the database transactions will start to time out pretty soon, because they're not designed to wait for that long. But if you do an async call, then the cache can be updated, and the database transaction will be completed. Again, keep in mind that the cache updates don't fail in the same fashion as a relational database. Why? Because a relational database can fail an update based on referential integrity or other data integrity violations. Cache does not check any of those. Cache is, every object is independent of other objects. So the only time a cache will fail updates is when some system failure happens, where something really goes wrong, which is not, which is different than the normal database transactions would be. So an async method would be called from a CLR procedure to go and do this. So those are three ways where you can ensure that the cache stays synchronized. So you need to take into account this really, really important aspect when you're starting to cache data. Unless your data is just read-only, then it doesn't matter. But if your data changes and it's a sensitive data, you want to make sure that cache is fresh. And the same rule applies. The cache should be able to synchronize with non-relational sources. So if your data is in mainframe, or maybe you're making some web method calls, you should be able to synchronize against that as well. So the cache should provide other hooks. So in case of NCache, there's a thing called custom dependencies. For other Java caches, they have other names. So the cache should provide some hooks where your code can be called, because only you know where the data source is. The cache does not know. So synchronize the cache with the database and synchronize the cache with the non-relational source. So you need to be able to do all of those to confidently use all types of data in a cache. And finally, I'll come to the question that you had, is that there's an added complexity with relational databases, is that different types of data has relationships. And because, unlike a NoSQL database where you aggregate data, so think of a Northwind database and order. If you had a NoSQL database, the entire order would be kept in one collection, right? You have the order and the order items all in one collection. Well, because the order items don't really exist independently. They're dependent on the order. But in a relational database, you would have two different tables. One would be an order table, one would be an order item table. So you have dependencies. So that's just one example. There are also other examples. So a relational database is known for relationships. So when data comes to the cache, you have different types of data. And if one data changes in the cache doesn't know if the other data is valid anymore. And so in case of an order is an example, if you had cached the order object and the order item object separately, and you remove the order from the cache, maybe you've deleted that order. Although, and you usually don't delete orders, but I'm just saying, as a hypothetical example. If that is the case, then the order items should not be kept in the cache. If you do, there's a data integrity problem. So that's where the dependency feature comes in. It's an ASP.NET Cache object feature, which NCache also implements it. But a dependency essentially allows you to tell the cache, this item depends on, so you'll say order item depends on order object. If the order object is ever removed or updated from the cache, please remove the order item automatically. So the application does not have to do any bookkeeping. Just like you are not used to doing any relational database bookkeeping. You don't maintain journals or any, data integrity details, right? You assume that your your database will take care of it. The same rule applies to your cache. You should not have to keep track of all of those data integrity things. So a cache dependency feature is also a very important feature, allows you to keep track of these types of data integrity violations. Any questions? Okay. So we talked about, so we've kept the cache fresh now. Okay. So now you're really starting to use the cache. It's become an important part of your application strategy, application architecture. So now, how can we make the cache more friendly, easier to use, to simplify your work? One of the features is read-through and write-through. Read-through is nothing but your code. Let me just show you an example here. So read-through is your code. Let's say you implement a read-through provider example. And again, the same concept exists in other caches too. I'm just using NCache as an example, at least on the Java side. So you implement a read-through interface. It has three methods in case of NCache. There's an init method, which is called when the cache is started, so it can connect to your data sources. It usually contains your connection strings and other things. There's a dispose method, which is called when the cache is being stopped, so you can disconnect the data sources. And there's a load from source method. Where'd that go? There. So there's an overload of that for bulk fetch. But let's say there's a load from source method, which takes a key and it gives out a cache item, cache item is the data structure which contains the data plus other metadata, like expirations and other things. So your code now goes to your database and gets the data. So this code that I just showed you will run on the caching tier. That means that your application has less and less of the database code. So you're actually using a cache as an encapsulation layer. So it simplifies your application. That's one benefit. The second benefit is that you can use read-through, for example, in other cases. For example, as we talked about expirations, right? That you're doing absolute expiration. You're saying, expire this 5 minutes from now. What does that mean? Expire means what? It means remove that item from the cache, right? But what if you just wanted to reload a new version of it? It was some pricing that was changing. So if you didn't have the reload option, the item would be removed, and let's say it's a really heavy traffic e-commerce application. So all of the clients will immediately hit the database. The first one that finds it will go and update the cache, but while that is being done, thousands of requests have made it to the database unnecessarily. Now, think of that. You've got hundreds of thousands of these items that keep expiring all the time. So you're sending a lot of unnecessary traffic to the database just because you don't have a reload capability. But if you could have a reload capability, what would happen? The expiration would not remove the item from the cache. It would actually call the read-through and say, go and get me a new copy of this. So read-through will get a new version of that because read-through knows, based on the key, it knows where to go and how to get that data. It'll reconstruct that object, that entire thing, give it to the cache, and the cache will now go and update that item. Instead of removing it, it just updates it. That means that the item is always in the cache. It just gets updated at expiration intervals. The same rule applies when you combine read-through with database synchronization. When the data changes in the database, why remove it from the cache? Why not just reload a new copy? Again, your application becomes much simpler. So read-through has the benefit of, first, simplifying your code because more and more of your database code goes into the caching tier. That way, if you have multiple applications sharing a common caching infrastructure, all of them can also share the code, so they don't have to maintain that code. And second benefit, as I said, is the auto reload in case of expirations and database synchronization. The second is the write-through, which is the write equivalent of read-through. It has, the first benefit is the same, which is the encapsulation. It simplifies, let me just show you the write-through. So this was read-through. This is the write-through. Same way, it's got an init method, it's got a dispose method, it's got a write to source. Now, write to source also tells you what the operation is. The operation could be add, update, or delete, right? I mean, the write could be one of those three. So based on that, you then go into your database source and you take the appropriate action. And then you can do the same with there was another overload of this, which was a bulk. So you could actually update multiple items at the same time, right here. So the first benefit of the write-through was the same as read-through, but the second benefit is actually different. The second benefit is, and this is actually a very important benefit, that you can use this thing called RightBehind. In RightBehind, the application updates the cache and does not wait for the cache to update the database. Why? Because database updates are slow. I mean, cache is at least 10 times faster, if not more, than a database operation. So why not just go and update the cache in a write-behind manner and tell the cache, please go and update the database for me. It's the same write-through handler that gets called, but now it might be called in a bulk, because it's going to queue up the stuff, and there are other variations that you can use. When you say go and do bulk update, you can do retries if the operation fails. But now your application does not have to wait for the database. Of course, when you do the write-behind, there's a callback that you can register. So if something goes wrong, you will be notified. So that if the operation fails and there's no way to actually perform that update, then you will be notified so that you don't have that situation where you think the update was done, whereas it wasn't. But the write-behind means that you no longer have to wait for the database updates. One more situation where your application becomes much, much faster. Of course, data that is very, very sensitive, you don't want to do the write-behind, you want to do the write-through. But a lot of data, you have enough tolerance that you can do the write-behind and really speed up the operations. So read-through, write-through is very, very powerful feature. Any questions? I've been talking nonstop.
Can you set up your caching tier in a sort of primary, secondary configuration where your updates go to a primary node in all instances, and only when a read isn't available in a secondary cache, it goes to the primary cache node first before it goes to the database. Thus, multiple clients use at the same time. Try and go by the primary cache node first before going to the database.
Okay. I can talk about NCache. Every cache has their own strategies. By the way, this feature, read-through, write-through, on the .NET side, only NCache has. On the Java side, you have other players that have it. In case of NCache, depending on what caching topology you're using, there are different caching topologies, but let's say if you were using this topology called partition replication, or partition replica here, where you can have multiple partitions, every partition is backed up onto a different server. What happens is, depending on what data you're updating, whichever partition that data is supposed to exist in, the read-through or the write-through runs on that server. So that way it can do distribution and load balancing, so that one server does not become a bottleneck. However, if you have a different topology, let's say there's another topology of NCache. I don't have that slide here because this talk was not about NCache. But there's another topology in NCache called replicated, where every server has an entire copy of the cache. So every server has the same data. So in that case, all the read-throughs and the write-throughs go to the primary coordinator of the time. If that server fails, then it goes to the next one and the next one. But in case of partitioned topology, it's much more scalable if you can distribute the read-throughs and the write-throughs to all the servers in the cluster.
Yeah, I'm just thinking because the reads are more common in our scenario than the writes.
Right. But even for the reads, again, keep in mind the read-throughs reads are being done when the cache does not have that data. In some cases, you can also force the read-through and say, even if cache has the data, please call the read-through. Because for whatever reason, you just don't want to take a chance on the read-through. In that case, every read will call the read-through. But in majority of the cases, read-through is going to be called only when the cache does not have that. So let's say you do a cache.get, and the cache does not have that data. So then cache will call the read-through. So the percentage of the time that you go to the database is that 20% as a bench or less. So did that answer your question?
Yeah.
Okay. Any other questions on the read-through, write-through? Okay. So let's say you're convinced about cache being a scalability solution. You're convinced about these use cases. You know how to keep the cache fresh. You're benefiting from the read-through, write-through. That means you're putting a lot of data in the cache now, right? So the cache can no longer be just a key value pair. Because if it were just a key value, even though that's how the cache is underneath, it's a key value pair. But if that remained as the only way to access the cache, you would have your applications will become much more difficult. So the cache has to start behaving more and more like a database. So one of the first things that a database is good for is ability to query, to search, to find data easily. Instead of finding it only on keys, you want to be able to find it on other attributes. So a good distributed cache will provide you with some sort of a querying language. In case of .NET, it's either SQL or LINQ querying. So you should be able to do something like select customers where customer.city is London, and get all the customer objects from the cache where that attribute condition is true. So the more you're able to do these types of searches, the more you're going to benefit from a cache as a database. The less you're able to do these, the more painful the application will become, because you'll always have to go to the database for these queries, and only for individual object fetches that you'll go to the cache, which defeats the purpose in many cases. So here, let me show you an example of how you would do SQL. Again, you would connect to the cache and do all the so whatever data you have in the cache, then you issue a query. In case of NCache, as I said, you just specify the object name or the object type, and you specify criteria. And the criteria cannot include joins, but it can include everything else. You can do in operator, you can do like, you can like wildcard, and you just do an execute reader, and just like SQL Server, you're searching the cache. And with this type of a capability, now you can load a lot of data in the cache. All those lookup tables can just be in the cache. Why go to the database at all? But even though you're loading all that data in the cache, you are able to search it in the same fashion as you would a database. So the simplicity of doing SQL type of querying makes your life a lot easier. The same thing goes if you like link, you can, and if the cache that you're using has a link provider, then you can essentially get your queryable, let's say here, and then you can issue a link query the same way as you would. Now, behind the scenes, that of course is being converted into SQL searching, and then a record set is being returned. So whatever you're comfortable with, whether you want to do link or whether you want to just do SQL searching, the bottom line is you should be able to do searching in the cache. Now, one thing to keep in mind, that when you do a SQL type of searching, the entire data set that you're searching on has to exist in the cache. So if you're searching for customers where the city is New York or London, all the customers have to be in the cache. Why? Because if some of them are in the cache, some are in the database, you don't know which ones you're going to get, which ones you're not. So that's an important thing to keep in mind. So SQL searching is good when you can load the entire data set, entire data into the cache, or that type of data, which is, again, a lot of use cases. Okay, we've got 4 minutes left. Okay. Similarly, because you cannot do joins, there are other things that you can do. You can do grouping. So there's a group, subgroup, tags, name tags features that allow you to fetch groups of objects back, which may, and you should be able to include this in the SQL criteria. So you should be able to do select customers where customer.city is London and customer.group is important customers. And then you can do tags also. So, for example, groups and tags. App Fabric had the tagging feature, by the way, but the grouping feature didn't. So you could do something like you can specify here, as you can see here, you can do a key value, key value group and subgroup. So in this case, value is also a string, which usually is an object. And so this is a group, and this is a subgroup. And then you can later on say, give me everything that belongs to this group, electronics, and then you can search on it. The same way you can do tags. So name tags are good when you, for example, want to index text data. When you do SQL searching, this searching is only possible if you do indexing. Without indexing, how are you going to find all those customers where city equals London? Because you don't want to deserialize every object in the cache, spanning, let's say, 5 cache servers, millions of objects, potentially, because you don't even know what the object type is yet. Unless you, so the time to index is when you're adding or updating. So on the client end, you extract that data and you send that as metadata with the actual serialized object and keep those indexes on the server end, and that's how you can search. So the same way you can do this, these also become indices. So because these are indices, you can actually do SQL. You can include these. You can say this.group is this .tag is this, or name tag is this. Name tag is essentially used when you have text which does not have attributes. So you can give it attributes that you want. There's one feature that I want to cover which is very important, which is called client cache. So, when you had standalone caching, let's say if you're using ASP.NET Cache object, it's all within your worker process. So you're used to super speed. Why? Because that object is being kept in an object form within your process on your own heap. Nothing beats that performance, right? So the first thing that a lot of people ask us is, Well, I plugged in NCache, or let's say whatever cache, and my performance actually went down. I was used to all those super fast fetching of objects, and now I'm making those calls across the network. Well, there's no way around the fact that you have to store these objects across the process or in another process. But there's a feature called client cache, which again, on the .NET side, NCache has, and on the Java side, you have other caches that have it. Some people call it near cache. On the Java side, that's what they do. And the client cache essentially gives you that benefit of a local in-proc cache. But you don't want to have that as an isolated cache. That cache is kept synchronized. So whatever is kept, so based on your usage pattern or whatever you're fetching, that copy is kept in the client cache as in an object form, so it's super fast. So you get that same performance, but now that object is being kept synchronized. So this is a very important feature, and I've crossed my time limit. Any questions on this? I'm going to stop the presentation. Any questions at this time? I would strongly encourage you. I was going to go into the last piece, which was the caching options for .NET. There are basically two options on the .NET side. One is NCache, one is Redis. Look them both up. On NCache side, that's the company I represent. I hope I didn't do a marketing job on NCache here. I hope it was a objective, technical conversation. But you can come to our website, go to the download page, and you can download either the Enterprise Edition or the open source edition. The open source is also available on GitHub. NCache is open source, so it's the same. So do take a look at both of these, NCache and Redis. There's also a lot of detailed comparison of NCache with Redis on our website that will make your life easy. But most importantly, please do consider using a distributed cache in your infrastructure. Make sure your applications are scalable. Any questions? Thank you.